the organization. I would like to thank all of the organizers sincerely. This is a really great organization. I had a chance to meet many people, and it was a great experience for me working with Selma. So thanks for organization. With Selma, we studied first course in topology, kind of what is topology, what are topological spaces, bases, subbases, subspace product, and we end our study with Hausdorff spaces. So, and we used Munker's book, and also Selma consulted other references as well during the our time in working on this subject. And now I let Selma to continue the thing, and then what she's going to talk is more about what is Hausdorff and non-Hausdorff spaces.
Yeah, okay, thank you so much, hello everybody, my name is Selma, and I'm in my final year in Middle Technical University. I'm a mathematical engineer, and it was a great experience to learn topology with my mentor. It was really hard to collaborate the different time zones in Canada. He was in Canada and in Turkey. But in addition to that, it was a really great experience for me. Today, I'm going to talk about, all of us are mathematicians, and we know that one sequence has to converge to one point, as we know. But in here, we're going to talk, we will talk in different fields. Everything will be different in topology. First of all, let us start with where is the topology. With my mentor, we studied where's the topology, and today we're going to talk about where is the Hausdorff space, and we will discuss about can a sequence converge to one than more value line. So, as we know, the topology is one of the central area in mathematics. In mathematics, we are focusing on geometry or any dimension, like specific dimension, when we study maybe something like about angle or triangle or something like that. Every dimension is important for us. But in topology, there is no dimension, there is no angle, there is no specific depth for a shape. We are only focusing on the shape. So what I'm meaning here is topology only focuses on the properties of the geometric object, which is topological space. Everything here can be a topological space, like this can represent a topological space. We are not caring about the length or the shape, or we are only focusing on the shape. And in topology, when we focus on this specific object, we can twist it, we can bend it, and we can press on it, but without without separate the shape, without separate it to like this, for example. This paper, I can bend it like that. I can twist here and when I bend it like that, this is a it's not clear, but this is a manifold. Manifolds. I'm sorry. And here in this paper, I cannot separate it to separate two paper. In topology, this is important because we cannot separate the two areas. We are only focusing on the specific plate here. So as I said, without any of the following occurring, creating or removing holes, tearing, I can tear, I can glue, or passing through it. And here, actually, we can see a donut here. And by the topological movements, as I said, we can bend it, we can do everything we want without separate something here. Here, we can see this. I can, let's start from here. I can, like, starting from this area, I can press and press and press, and so on. I can make this. So actually, I didn't separate anything. I didn't focus it on that, like, specific length or specific angle. I always try to make a new, deformation for the shape by your imagination. This is only includes in contains in topology. So that will a short introduction about topology. So let us define what is the topological space and what is the topology in mathematics, because it may be some abstract topics, but like that. So firstly, when we define a topology, we have to think about a set. There is not condition to be a set of like a numbers or a sequence or something like that. We can define a topology here on like on a set of our numbers here, or like set on a country in the world, or set on the language in the world. We can define a topology if we satisfy this condition, as I say. So let us define X. Let X be a set. There is no condition, as I said. And let T be the collection of subset of T. The collection of subset of X. So I can define a topology on X, and the pair xt will be a topological space. So if I have to define a topology on X, we have to satisfy these following property. Firstly, we have to, like, let's imagine that we have X and we have T, and T is the collection of subset of X. So eventually it has to contain the empty set and X the whole set. At the same time, we have, if we choose randomly two subset from T and intersect it, if I intersect it, I have to find the same intersection in T. And if I select randomly two subsets from T that I define it on X, if I take these two subsets, the union of those two subsets has to be belongs to T. On the other words, the union of arbitrary collection of elements of T belongs. And the intersection of any finite number of elements on T of T belongs to T. So when we satisfy the following the above properties, we can say that okay, we are able to define a topological space on X, and any set belongs to T has to call it is called it open set. So when I say open set, it means that any set belongs to T, which is defined on X and created a topological space. In general, we can define a lot of topological space in real number. When we define a T, when we condition the T or restrict in certain condition, we can define a lot of topology, like standard topology. We can define discrete topology, or there are a lot of topology where we can define it. For example, when we define T as a power set of X, let's try to imagine that T will be very huge, very general topological space, because T is the power set of X. So any subset in X, any small part in X has to belongs to T. Or when we let us define T as only X and empty set. So now let us try to imagine the difference between that. As I mentioned before, when we define T as a power set of X, the topology will be huge. But when I define T as only X or empty set, the topology will be so narrow. This is only abstract. And we decided with my mentor to mention about standard topology. Thanks to my mentor, because it was really hard to handle this graph. And the standard topology, actually, we can define it on any set that we have. But especially, we define the standard topology on real numbers. We can define, as I said, the standard topology. We can, we can define a standard topology on real number, and so we have to specify the condition. What kind of topology we have to find on that? The standard topology is considered as an open interval in real number. Like any open interval has to have a neighborhood, like epsilon. Here we can, as we can see, Q is subset of R, such that any open, any open interval has to be a subset of U. U is any open set belongs to T. Okay. So here, as I say, to be able to define a topological space or any set, we have to satisfy the two conditions that I mentioned before. Any two, I selected here any two open intervals. I have to intersect it, and if I intersect it and find the same intersection in T, then I can define the topological space. At the same time here, just consider like open interval from A to B and open interval from B to C. When I intersect it, I will find the open interval. So that will be belongs to T at the same time. And when I make the union of combine these two intervals, like from A to B and B to C, it's so easy to understand that this interval will belongs to T at the same time. So here we're trying to understand how to satisfy the properties to define a topological space. I said we don't have to define a topological space on a specific number or any specific object. Here, I defined the topology of X, and X have to be A, B, C. So let us consider this question. Let T be an open set, empty set, A, B, and B, and B, and C, and X. So now our question is, can we define a topological space on this set? As we state here, let us consider this first circle and this one. So when I choose these two sets, I will take the arbitrary union of two sets, which will be A and B. And A and B, which is in T, belongs to T. Okay, so I have to satisfy the property on all members, on all subsets on T. This is important. Like, or some, let us choose this circle and this one. When I take the intersection of two subsets, I will find an empty set. So this belongs to T. At the same time, when I choose the whole X, will be in T at the same time. So here we can say that we can define a topological spaces by this scheme to imagine more easier. And this is one of the most what we focused on it with my mentor, finite complement topology. So finite complement topology, and we can understand what kind of topology here by the name. Any subset, any set in T, has a finite complement in topological space that can be considered a finite complement topology. For example, let us consider this real number. From this real number, I can separate, like, we can imagine that only remove one whole from the real number. It's not like, we don't have to think only on real number, but here we define it, but here we define the finite complement on real number because that was we're focusing on. Let us remove one point from this. I can remove 2 and 3 and 4, like x1, x2, and so on. So I defined U, and I said that U have to be a subset of T, like open set, on other words. And this U has to be a finite complement, has to have a finite complement in this topology. So when I think this, by the definition, I remove the certain whole from the real numbers. and that will be defined, finite. Do I have to clarify anything here? So here, let us define the same properties here. If I remove only one whole, imagine that we removed only one like xn minus 1. And this is u. And imagine that I removed from the real number some set like v and removed like 2 or 3 points. When I intersect these 2 points, I will find the finite value because there's no infinite value here. At the same time, when I intersected, as I said, when I combine these 2 sets, I will find, I will remove the whole from real numbers, so I will find a finite complement here. I will find a finite value in this topology. And let us consider what is the Hausdorff spaces. Actually, after we considered what is the topology, how to define topological spaces, and what is the finite complement topology. Our goals in this presentation is to understand how to examine the Hausdorff topology and how to consider what kind of sequence can approach to more than one value in Hausdorff spaces. Hausdorff spaces, it's like so abstract thing because we can imagine it in our brain. And then let's define X and T. Let T be a topological space. Okay, let's find the neighborhood first. This is important. Before starting to defining a Hausdorff topology, I would to define what is the neighborhood in mathematics, in topology especially. In topology, a neighborhood, when I consider any open sets in a certain point, like imagine that we have X, we have T, and we choose as randomly one point from this topological space. This point, any open set, like any open set, when I say any open set, any set belongs to T. Any open set contains this point can be considered as a neighborhood of X. Any point is not important. So neighborhood in topology can be considered as any open set contains that point, which has to belongs to topology. On the other words, given a topological space X and T, a neighborhood U is an open set of a point X is an open set containing X, such that U, as I said, has to be in a topological space. So our Hausdorff topology, Hausdorff space is something like, imagine that we have X and we define a topological space XT. We have XT topological space. Imagine that we choose a random 2 points from X, like X1 and X2. Let be X and Y. And I choose a random neighborhood. It's not important. A random neighborhood from X contains X and Y separate. Now, my question is, can I separate these 2 points? Can I separate the neighborhood of these 2 points here? My question is something like that. Because like if we try to imagine that in a real number, try to like consider 2 and 4. I can choose any open set, like I can choose an open set, a neighborhood of 2, like very small in the area here. And the 4, I can choose very small neighborhood at the same time for 4. And I can separate these 2 neighborhoods from each other. But in topology, it's very important. It's completely different. When we consider a convergence or of any sequence in a real number in calculus, we are only focusing on like a very small area, which is epsilon. We can go smaller and smaller and smaller to find what is the value converges to. But in topology, it's important because we don't have enough open sets, like enough neighborhoods to specify what kind of value are approached to it. So here, let us consider the standard topology. As I said before, if we consider any two real number, and we can separate the neighborhood of two real number easily, because I can choose very smaller neighborhood from them, because there is no condition. And here, this is a very simple example about house of topology. Here, we define X and we define T, as you see, and if this space is the house of space or not. We are, if we have to find is the space the house of or not, if we can separate 2 points, we have to choose 2 points randomly, and we're gonna think about the neighborhood of 2 points and trying to separate it from each other. Like here, let me choose C and B. So any neighborhood contains C, it means that this circle and the whole set. Let us consider B. The neighborhood of B can only be any open set contains B. By definition, can be this circle, or the whole set. So here, when I'm considering about the neighborhood of C and the neighborhood of B, I cannot separate it from each other here, because the neighborhood of C, by the definition, is the neighborhood of B at the same time. Did we understand? I can clarify. Like here, we choose A and B. The neighborhood of B is this small circle. And the neighborhood of A, which is any open set, involves A, which is this circle and the whole set. So here, as we say, we cannot separate the neighborhood. I mean, what I mean by separating is only one neighborhood contains 1 point here, one open set. This open set, okay, involves only B, but this, when I'm considering the neighborhood of A, I consider the neighborhood of B at the same time, because the neighborhood of A involves B. So these conditions are here wrong, so I can define a house of spaces here, because I cannot separate. The condition has to be satisfied by the all point here. If one point is not satisfying the property, that will wrong. Okay, and now which is our goal. Sorry. The finite complement topology, as I say, is any open set has a finite complement. And the finite complement has to be open set. As I said, open set is means any subset belongs to topological space. And the finite complement topology is not house of space. Why? Let us consider that. As I said, a finite complement topology, any open set has a finite complement, which is mean that U, I consider it U and V. U has to be finite because U has to be an open set in finite complement topology, which means is U has a finite complement. As we said, we removed a certain whole from R, from real number. Sometimes I consider it V, complement topology. By the definition, if I have to define a house of spaces here, I have to separate, to be able to separate any neighborhoods from these 2 points, like U and V. If U and V are disjoint, by the other way, if U and V are disjoint, then we can define a house of spaces here. But if we consider that real number is an infinity, and it is impossible to remove, like to say that U and V are disjoint, because it's impossible, because I can remove the same point here, and we may face with any intersection. So that is important. So here we can say that the finite complement topology is not house of space. So as I said, when we consider a convergence in a sequence, we have to think about the neighborhood of any number, of any point. Like here, as I said, we know that in mathematics, the sequence has to converge to only one number. because we can find the open set, very small neighborhood of a number, and we can find the specific points, like what kind of point that converges to. But here, as I say, in topology, it's very different. Because here, let us consider 1 over n. Let us define a sequence 1 over n. And this 1 over n, as we know, converges to 0. But in non-Hausdorff space, converges not only to 0. Converges to 1, converges to 2, and to all real numbers. To define that, let us consider this example. Like, let's hear, no. Yeah, that's good. So, as I say, let us consider that 1 over 9. 1 over n, a sequence. My claim is 1 over n has to converge to 1 or to 2, 3. Worse, it's not important. Okay, to improve that, let us define this sequence in a finite complement topology. And a finite complement topology, as I say, is an open set, has a finite complement. So here, now as I say, for example, 1 over n, my claim is 1 over n has to converge to t in a real number. So I have to prove that any neighborhood contains 0 has to contain 2 at the same time. Because if all neighborhoods contains 2, that means that the sequence converges to 0, to 2 at the same time. Because all neighborhood contains 2. So I can say that the sequence converges to 2. So here, let us define U. Any open set, any subset in a finite complement topology, and has to contain 2. And when I consider the finite complement here, you can consider this red line. So as I said, the sequence has to converge to 0. But I choose now, I decided to converge to 2. Let us consider a point between 0 and 2, which is xg. So if I will be able to define that, yeah, there is one xg, like I can go smaller and smaller, I can explain that 0 has to converge to only one set, to only one point. So here, as I say, the element xj determines the positive integer n, which means that I can get closer and closer and closer. But in this open set, it's not possible here. To imagine, let us show here. Imagine B is the 0 and A is the 2. Okay? So any open set, all open set, when I define a convergent in a sequence, all neighborhood of a point has contained the same point. Like, I decided to show it maybe. Imagine that this is a sequence and this is a point has to converge in it. So our sequence, all neighborhoods, like imagine that this is going for the infinity. After a while, all values or this sequence has to converge in different. And when I choose any randomly neighborhood, I will contain this point, which means the sequence converges to this point. But in the topology, it is different. Because when I choose, imagine that this is 0 and this is 2. Okay, let us consider the neighborhood of 0, this circle, this set, and the whole set. When I consider the neighborhood of A, this circle, and this circle. That means we have, in the neighborhood of B, or the neighborhood of 0, we have A at the same time. Because when I consider the neighborhood of B, the whole set, and this set. So A is the same place of this set. At the same time, when I consider C, it can be at the same neighborhood of B. And this means that in any sequence can converge to A, B, C, and all numbers. This is very different fight that we are get used to think about it in general calculus, because there is no condition. Here, we cannot define any open set that only contain B. Okay, we define this set, but at the same time, the neighborhood, all neighborhoods of B contain A, contain C, contain the all sets. So that's why I proved here that any set can converge to one blank value in a non-Hausdorff space, because there is a condition, there is a restriction. Thank you so much. And if you have any question,
Are there any questions? We don't have so time, but we can almost we can. Are there any questions?